Hello everyone, welcome to this video. In today's video, we're going to be dealing with non-steady state mass and energy flow in a tank of water that I've already drawn here. So to start, we basically have to assume that the water within the tank is pure and perfectly stirred with the help of the mixer. And we will know that the water has a height that we can call H and a cross-sectional area that we can call A. There is also water flowing into the tank at a rate that we'll call QN, and water flowing out of the tank at a rate that we'll call Q out. So the water flowing into the tank is flowing in at a rate of 1 cubic meter per second. And is also at a temperature of 320 kelvins. While the water that's flowing out of the tank is flowing out at a rate of a constant alpha times the height of the water to the 1/2 power. And we also have to identify the conditions of the water that's already inside the tank. The initial temperature of the water inside the tank is 300 Kelvin. The cross-sectional area is 1 meter squared. And the initial height is 1 meter. So we can first find the equation for the change in height with respect to time by applying a mass balance onto our system. And to do this, we first have to know that the change in the mass of the system with respect to time is equal to the mass that's coming into the tank minus the mass that's leaving the tank. And when we look at the mass, the change in mass with respect to time, we are creating a mass flow rate. So it should be in units of kilograms per second. So from here, we can look at the left-hand side first. And we know that the mass of the system is actually equal to the density of the liquid, which is pure water, times the volume of the tank that it's in. And while the volume isn't explicitly listed, we know that volume is the area times the height. So we can rewrite our term on the left to be the change in the density of water times the area times the height with respect to time. And for our terms on the right, we'll know that the mass coming in and the mass going out are both the density of water times the flow rate coming in and the flow rate going out respectively. So the mass coming in is equal to the density times the flow rate coming in minus the mass going out, which is the density times the flow rate going out. And we know that this matches up because the units for density are kilograms per cubic meter. And the units for our flow rates are cubic meter per second. Obviously, our cubic meters cancel out, and we're left with kilograms per second. As we have in our first equation. But you'll also notice that there's a density variable in each term, so we can go ahead and cancel that out of each term. And we're left with the change in the area times the height with respect to time is equal to the flow rate coming in minus the flow rate going out. And so we can actually do a little bit more of cleaning up here. We can actually take out the area because the cross-sectional area is constant. And this actually works to our advantage because we are looking for the change in height with respect to time. So by taking out the area term, that is the derivative that we want to receive. So it's still the same thing, but we are just kind of singling out the area because then we can divide both sides by it. And so our flow rate coming in stays the same, but for the flow rate going out, instead of writing Q out, we can actually substitute this expression here for it, which is alpha times the height to the 1/2. And as I mentioned, all we have to do now is divide both sides by the area. So that we have received the equation for the change in height with respect to time, and it's equal to the flow rate coming in minus alpha times the height to the 1/2 power divided by the cross-sectional area. So now, when looking for the change in temperature with respect to time, we can apply an energy balance to our system. So we know that the equation for our energy balance is the change in mass times the internal energy plus kinetic energy plus potential energy. And that'll be equal to the enthalpy plus kinetic energy plus potential energy coming in times the change in mass coming in. And the same enthalpy plus kinetic energy plus potential energy going out times the change of mass going out. Plus the change in heat, plus the change in work, or excuse me, the change in non-flow work from the mixer. And for clarity, I've listed the height as capital H because enthalpy is lowercase h, and I listed the heat as capital Q because we have flow rates as lowercase q, so we don't want to mix those up. So for simplicity of this problem, we are going to ignore kinetic energy, potential energy, and the non-flow work. And so by ignoring these things, we've eliminated a good portion of our energy balance equation. And so because of that, we can rewrite this equation as the change in mass times the internal energy of the system equal to the enthalpy coming in times the change in mass coming in minus the enthalpy going out times the change in mass going out. And so if we were to divide both sides by dt and, evaluate the equation with respect to time, we would receive the same mass flow rates that we got in our mass balance when looking for the equation for our height of the water. And so we can rewrite this so that the change in the mass times the internal energy of the system with respect to time is equal to the enthalpy coming in times, again, what we received in our mass balance, which is the density times the flow rate coming in, minus the enthalpy going out, times the density times the flow rate going out. And so we can also do the same thing to the left-hand side, because we know, as we did in the mass balance, that the mass is equal to the density times the volume, and the volume is equal to the cross-sectional area times the height. So we can rewrite this as d times density times the cross-sectional area times the height times the internal energy of the system, all with respect to time. And again, we have a density term in each of our individual terms, so we can erase that. And cancel it out from each term. We can do some more tidying up by kind of taking out our cross-sectional area and converting our flow rate going out into its expression, alpha times the height to the 1/2. So I'll go ahead and do that. God, okay. From here, we can tidy it up a little bit more by taking out our cross-sectional area from the derivative and rewriting our flow rate out in terms of alpha and height. And this is where we really get stuck, but we can recall some things to help us. And the first step to that is knowing that we are dealing with a liquid, and the enthalpy equations for a liquid is dH is equal to the heat capacity at a constant pressure times the change in temperature. And the equation for internal energy is du times the constant, or the heat capacity at a constant volume times the change in temperature. So the internal energy and temperature both have to be evaluated at some reference point. So the internal energy of the system is equal to the internal energy at some temperature minus the internal energy at some reference. And that's equal to, obviously, the heat capacity at a constant volume times the temperature minus some reference temperature. And so usually we can say that our internal energy reference and our temperature reference is 0. However, say for instance, we didn't say that the temperature reference was 0. All we would have to do is put this expression in for the internal energy of the system, so that we have A times the change in height times our constant volume times T minus T ref with respect to time. And we can implement our equation for our enthalpy, so that we have the constant pressure times T minus T ref times the flow rate coming in minus Cp times T minus T ref times alpha times the height times 1/2. And this is coming in and going out. And so because this is a liquid, we also know that the constant pressure or the heat capacity at a constant pressure is equal to the heat capacity at a constant volume, which means that these will cancel out. And we can do even further cleaning up by actually implementing the temperature reference point as 0, so that these temperature terms just becomes T minus 0, T minus 0. So we can just write T. And so we can rewrite this as A times the change in height times the temperature with respect to time is equal to Tn, or the temperature coming in, times the flow rate coming in, minus the temperature going out times the flow rate going out. And we can divide all of this by our cross-sectional area A. And so from here, we are going to want to isolate the change in the temperature with respect to time. So to do that, we're going to apply the chain rule to our derivative on this side. So I'll bring this over here. And we'll get the temperature times the change in height with respect to time plus the height times the change in temperature with respect to time is equal to the right-hand side temperature in times the flow rate coming in minus the temperature out times the flow rate going out divided by A. And so all we have to do to isolate the change in temperature with respect to time is subtract the temperature times the change in height with respect to time and move it to the other side and divide both sides by the height. So we're left with the change in temperature with respect to time is equal to the temperature coming in times the flow rate coming in minus the temperature going out times the flow rate going out, which is alpha times the height to the 1/2 power divided by A minus the temperature times the change in height with respect to time times 1/H. And this is our equation for the temperature of the water in our tank. And now we're going to head over to Colaboratory so we can code this using Python. So to start coding the first part of this problem, first we're going to have to import all of our functions, starting with NumPy. So we'll do import NumPy as NP, and then do from SciPy integrate import solve IVP, and then from Plotly subplots we're going to import make subplots, and we're also going to import plotly.io as PIO, and finally we're going to do pio.templates.default as plotly dark so that the background for our plots is dark instead of light. And we're going to run that line of code. And so all of the functions that I've imported are probably familiar because I've used them before in other codes for some of the problems that I've done previously on my channel. But the one that probably looks unfamiliar would be SciPy integrate solve IVP. So to explain briefly, SciPy integrate is solve IVP is a function that can integrate a series or a set of ordinary differential equations given an initial value, which is perfect for what we're doing today. So before we do anything, we have to define and list our variables that we used. So we know that the initial temperature of the water inside the tank, which I'll list as T lowercase o or T naught, is equal to 300 kelvins. The initial height is equal to 1 meter. And the cross-sectional area is equal to 1 meter squared. We also know that the temperature of the water flowing into the tank is at 320 kelvins, and that water is flowing in at a rate of 1 meters cubed per second. We also have a constant alpha that will be equal to 0.4, and Later on in this problem, we're going to need to define a time span in which this problem takes place over, the time in which the water is flowing into the tank and out of the tank. And so we're going to have to define that as T end. And we're going to want a range of 100 seconds. So I'll set that equal to 100. So now that we've defined our variables, we can go ahead and start solving this problem. But first we have to define our function, which will enclose our differential equations for the height and the temperature of the tank with respect to time, or the height and the temperature of the water inside the tank with respect to time. So we have to define the function, and I'm going to call it BAL, or BAL for mass and energy balances. And we also have to identify our independent and dependent variables. We know that our independent variable would be time, so lowercase t. And we know that our dependent variables are the height and the temperature of the water in the tank. But instead of listing two separate variables, because that'll get really messy and we want to be, efficient and effective within our code, I'll just use one overall variable that I'll call D for dependent, and then within our function I'll unpack that variable and set it equal to both of our dependent variables, the height and the temperature, and then set it equal to D. And so now we can define and list our two differential equations for the height and the temperature, which we know to be dH is equal to the flow rate coming in minus our flow rate going out, which is alpha times H to the 1/2 power, and that's all divided by our cross-sectional area. And then the equation for our temperature, change in temperature, is equal to the temperature coming in times the flow rate coming in minus the temperature of the water coming out, which is just equal to the temperature of the system, times alpha times H to the 1/2 power, because that's just the flow rate going out, like we see in the equation above. And all of this is divided by the cross-sectional area. But we have to now subtract the temperature times dH. And then we have to divide all of that by H. And now that we've done that, we can return our differential equations in an array by doing NP array dH dt. So now that that's done, we can actually implement our initial value problem solver for the differential equations. And we're going to set that equal to solution, or SOL for short, and do solve IVP. And now we have to list or identify our function, which is BAL. And then we have to indicate the time span that we want to have the problem occur during, which is 0 to 100 seconds, which is T end. And then after that, we have to list our initial values, which we know to be T naught and H naught. But we also have to be careful because since we called the height equation first, we have to list H naught first and then T naught second. So we'll do NP array, H naught, T naught. Then we have to identify the method, which is Radeau, and the dense output, which is true. And get the solution of that. And so we're going to need to pick points over the time span that we chose. So we'll do t-plot, and this is, specifically intentionally for the plot that we're creating. And we're going to want to linearly space all of these plots from 0 to t end, and we'll pick 300 points for our plot. And so now we're going to want to evaluate the solution that we got using our initial value problem solver at those time points that we just picked. And since we are picking points for two separate plots, we're going to list both dependent variables h and t and then set them equal to the solution evaluated at our time points. And so now we can actually begin creating our plots. So we'll set our figure equal to make subplots. And since we want our plots side by side, we will do one row but two columns. So for the first graph or plot, we'll do fig add scatter, and our x-axis will be equal to t-plot. The y-axis will be equal to h, and then it'll be in row 1 and column 1. And the same thing, almost the same thing will go for the second plot. So we can copy and paste it. The x-axis will stay the same, but the y-axis will be for the temperature, and instead of it being column 1, it'll be column 2. And here are our graphs for the change in height and temperature of the water within the tank with respect to time. As we can see, the height of the water starts stabilizing at 6 meters around the 40 to 60 second mark, and for the temperature of the water, it starts stabilizing to 320 Kelvin around the 15 to 25 second mark. So in part 2 of this problem, instead of solving for the change in the temperature of water and having warmer water coming into the tank, we're actually going to be having water coming in that has a solute in it, and that solute has a concentration of 1 kilograms per cubic meter. So I've changed the temperature coming in to the concentration coming in and wrote the appropriate value in units. And again, that's 1 kilograms per cubic meter. And instead of us identifying the temperature of the water in the tank, we know that there is already some solute within the water in the tank, and that is sitting at a concentration of 0.1 kilograms per cubic meter. And so we are actually able to keep the equation for the height of the water that we got from part 1 of this problem. And the reason that we can do that is because I have labeled here the assumption that the density of the system is equal to the density coming in, that is equal to the density going out. And the reason why this is important is because we know that in part 1 we were taking or using the density of pure water. But since there is a solute within this water now that has a concentration, we cannot necessarily say that the water is pure. And in certain instances, there will be substances that are much heavier than water. And so the density of the system will not be equal to the density coming in, and that will not be equal to the density going out. But for this case, we're able to make this assumption and keep our equation for the height of water, which is amazing. So now we have to look for the equation for the change in the concentration of the solute with respect to time. And in order to do that, we're going to start with the same premise, or excuse me, the same equation that we did here, which was the change in the mass of the system with respect to time is equal to the mass coming in minus the mass going out. But this time, instead of the mass of our system being equal to the density times the area times the height, it'll be equal to the concentration of solute B times the area times the height. So I'm using capital C for concentration times the area times the height divided by, or with respect to time. And the same will apply to the mass coming in and the mass going out. Instead of it being the density times the flow rate, it'll be the concentration times the flow rate. And so the mass coming in is equal to the concentration coming in times the flow rate coming in minus the concentration going out times the flow rate going out. And even though we don't have the concentration going out listed, we can assume that the concentration of the system is equal to the concentration going out. And the reason that we can assume that is because, again, this water in the tank is perfectly stirred. That did not change. Even though we added a solute to the water, it's still perfectly stirred, so it'll be consistent as it leaves the system. And so from here, we can do the same thing that we did with our mass and energy balances. We can take the cross-sectional area out and divide it through both sides, so that we're left with the change in concentration times the height with respect to time is equal to the concentration coming in times the flow rate coming in minus the concentration going out times the flow rate going out is divided by the cross-sectional area. And this should look very familiar. Literally the only thing that we have to do is apply the chain rule to the derivative on the left-hand side so that we can isolate the change in concentration with respect to time. So that'll end up being the concentration times the change in height with respect to time plus the height times the change in concentration with respect to time is equal to our right-hand side. And all we have to do to finish is subtract the concentration times the change in height with respect to time from both sides, so we can move it over here. Actually rewrite our flow rate out as it's alpha times height to the 1/2 expression and divide both sides by the height. And so we are left with the change in concentration with respect to time is equal to the concentration coming in times the flow rate coming in minus the concentration going out times alpha times the height to the 1/2 power divided by the area minus the concentration times the change in height with respect to time, all times 1 over the height. And this is our equation for the concentration of solute B in water. And now we can head back on over to Code Laboratory so we can code part 2 and finish the video. So coding the last part of our problem is really simple. To find the change in concentration of our solute B, because it's essentially, as I mentioned, it's essentially our temperature equation that we derived. So all we really have to do is include our initial concentration values and substitute our temperature variables for concentration and create our plots. So the first thing we can do is change T naught to C naught and make it 0.1 kilograms per cubic meter, and then change Tn to Cn and make it 1 kilograms per cubic meter. And from here we change our dependent variable T to C. We change DC to, or excuse me, DT to DC, TN to CN, and essentially anywhere we see a T, we change it to a C, which makes this really convenient. Again, our initial value is C naught instead of T naught. Oh gosh, okay. And that should be all. And so we can run all of our new lines of code. And we get our plots for the height of the water in the tank and the concentration of solute B in the water in the tank with respect to time. It stabilizes, the height stabilizes at a little bit above 6 meters at the around 55 to 65 second, 70 second range. And the concentration of solute B stabilizes to 1 kilogram per cubic meter from around the 15 to 25 second range.